Hello, my name is Riley Tharp, team lead for the robotic walking training device. Each year, nearly 800,000 people suffer from a stroke, and over half of these cases result in the patient losing the ability to walk with a normal gait, while approximately 300,000 individuals suffer from a spinal cord injury that impairs their mobility. The purpose of this project is to create a rehabilitation device which can help these individuals regain their proper gait. This is accomplished through robotic legs which are mounted to a lift which serve to move the patient's legs in a normal gait path. This is used in tandem with a functional electrical stimulation device used to stimulate damaged neural pathways while the step is being taken, with the hope of retraining these nerves in time with the muscle movement to better aid in rehabilitation. The natural gait of a human consists of an arc motion for the knee and a horizontal teardrop shape for the ankle. Our goal was to recreate these paths to within 10% accuracy measured with the motion capture system. Our device must also accommodate patients of all shapes and sizes, from 5 foot 0 inches to 6 foot 4 inches and up to 300 pounds. Lastly, we need to electrically stimulate the thigh muscle in conjunction with the walking motion in order to improve muscle function. Our budget for this was $2,000 and was considered the primary constraint to our design. Additionally, we had to satisfy our customers' specifications such as obtaining all required resources for construction and simulations which proved our design prior to manufacturing the system. Our device has 4 main components. First is the scissor lift, which serves as the base of the device and uses a linear actuator which allows the patient to be raised or lowered to various angles depending on their level of rehabilitation. Second, the arm supports, which are adjustable and provide support and security while the device is in operation. Next is the FES system, which will be used to stimulate the thigh muscle as previously mentioned. And finally, the robotic legs, which are the heart of the device and provide the necessary assistance to recreate the desired gait path. This is accomplished through a motor and pin assembly at each major joint, which drives each leg link. 6 motors were used to drive the linkages at each joint in order to recreate the gait path. These linkages were constructed from aluminum, which was chosen due to its machinability and robustness. The pivot pins at each joint transmit the force from the motor into the respective linkage. The motors were selected due to their high torque, which exceeds our calculated requirements, which will reduce system fatigue. The appropriate waveform for the FES was determined through research in the field of rehabilitation. It was found that a high voltage pulse between 0 and 500 milliamps for a period of 15 to 30 minutes has been shown to re-educate peripheral nerves and limit muscle atrophy due to the contractions produced by this therapy. This was deemed an effective rehabilitative process for this device. As this is the 3rd generation of this device, several upgrades were made to prior iterations. The most obvious upgrade was to the leg assembly itself. Previously, plastic linkages were used and the device operated much like a reverse bicycle. The new assembly was constructed from aluminum for the linkages and steel for the pivot pins to provide more stability and longevity. The device now functions as an exoskeleton, driving each joint individually. This allows for greater optimization as well as adjustability. The gait path was achieved by using a planetary gear-driven DC motors with Hall effect encoders, which were connected to each link and are individually controlled by their own Arduino microcontroller. These allow for each link to be moved in the desired range of motion and can be easily customized for a more accurate gait. The base was redesigned as a solid steel plate with 4 steel posts and resting on 4 large casters. This design helps to offset any instability which could occur as the device is operating. In addition to structural improvements, items were added such as adjustable arm supports, memory foam padding, and straps for patient comfort and safety. The only recycled item was the scissor lift, which received an upgrade in the form of a linear actuator, rather than a manually operated hydraulic pump, for smoother transitions from prone to upright positioning. To sum up, our goal was to design a device which could help to more effectively rehabilitate victims of SCI or stroke who have lost mobility in their legs. This device aims to accomplish this through robotic legs mounted to a base which moves the patient's legs in a natural walking gait while stimulating their thigh muscle in time with the step using an FES device. Analysis was performed to determine the necessary path, materials, device stability, and maximum forces experienced during operation. Simulations were performed which proved the design choices by showing that the leg assembly would move in the correct path without any interference. The scissor lift will raise and lower without failing, and the arms provide sufficient support under maximum loading. Thank you.